Hello everyone. Mm, Now let us discuss the concepts of polar plot and Nyquist plot. Before going into details, let me give a brief description of few basics that will be helpful in plotting these two topics. So basically, there are two types of things here. One is contour path. Another thing is functional plane. If there are two poles in this contour path and the given direction is, let us say, anti-clockwise, then projecting these two poles will get two encirclements in this functional plane this way, and the given direction is anti-clockwise. So for anti-clockwise direction we'll give n value positive. For clockwise direction we give n value negative. So here in this case there are two encirclements, so n value is 2 and the direction is anti-clockwise, the sign is +2. Similarly, if there is 1 0 and the given direction is clockwise direction, in the functional plane we will get one encirclement with given direction clockwise, so n value will be 1 for one encirclement, clockwise direction for minus. So what if we have both poles and zeros? Let us say there are two poles, three zeros in this given example. Then here, so these two poles and two zeros get cancelled, then one zero is left. So because of this 1 0 we will get one encirclement, and obviously given direction is clockwise, so n value will be 1 for one encirclement and -1 for clockwise direction. Now let me give this important formula. This is the very important formula in this stability criteria, Nyquist stability criteria. Here the formula is n is equals to p minus z, where n is the number of encirclements in Nyquist plot and p is the number of right-handed poles, and z is what we need to calculate using these n and p values. If z is equals to 0, the system is stable, the given characteristic equation or transfer function is stable. If z is a non-zero, then the given thing is unstable. This is the known as Nyquist stability criteria. And now let us discuss the important part of this Nyquist plot and polar plot, that is Nyquist path. See, there is a difference between Nyquist path, Nyquist plot. Seeing the Nyquist path, we will draw Nyquist plot. This Nyquist path is also called as Nyquist contour. So there's a basic or predetermined Nyquist path, Nyquist contour is this thing. Let us consider this point A, B, C, D. This is in the form of r e power j theta, like we are representing in the form of polar form. So this is imaginary axis plane, this is the real axis sigma. So we are dividing this Nyquist path into A, B, C, D. So let us discuss how should we plot this AB part, BCD part, DA part. Summation of these three parts will give you the Nyquist path. So first thing, how to calculate part AB. Calculation of part AB, like if let us say the given transfer function is this, some transfer function. Now there step-by-step procedure is substitute s is equals to j omega in given OLTF. Now this OLTF of j omega, now find the magnitude of open loop transfer function also find the phase of the open loop transfer function. Now, using this magnitude and phase expressions, varying the value from 0 to infinity, find magnitude and phase, and then plot this magnitude and phase in the S-plane. See, polar plot is plotted in S-plane. Nyquist plot is plotted in G of S, H of S plane. Let us go about these details in detail later. And now so far we have completed this AB part. Now let us go to DA part. DA is symmetrical about x-axis to AB. So let us say if the AB part plot is this, then the DA part plot will be this. That means DA and AB are symmetrical. So once you calculate the part AB, you will automatically get the part AD. So now you have calculated AB, DA. The remaining part is BCD. There is one rule in plotting this BCD part. If number of poles greater than number of zeros, then BCD will be always a point at origin. You will get much clarity while solving this problem. So now we have done these three parts. These three parts comprises of a Nyquist path. See, plotting this AB alone is polar plot. Only AB part is known as polar plot, and summation of AB, BC, D and DA will give you the Nyquist plot. This is the difference between polar plot and Nyquist plot. And now this is the case where there are no poles in this part. But what happens if there is a pole at origin? So we can conclude that there are two cases in this Nyquist path: without a pole at origin, with pole at origin. This is without a pole at origin. So what happens when there is a pole at origin? So this is the contour when there is a pole at origin. While plotting, we will avoid this part like this. So now the parts will be A, B, C, D, E, F. So in this we have already studied about AB. We have already studied about AB, BCD, DE. That is nothing but symmetrical to AB. And now the new thing is EFA. This is also simple, nothing to worry here. In order to plot EFA, there is one small table. If there is one pole at origin, that is 1 by S, your plot will be a half circle. And let me write here. 1 by S, half circle. That is this thing. If there are two poles at the origin, you will get a full circle. That is this. If there are three poles at the origin, you will get one full circle plus one half circle. Like this way. So finally, we have studied the basic steps to plot the Nyquist plot. Let us do few problems to get clarity. So now let us do a simple problem. 1 by S plus 1 into S plus 2. So therefore there are no poles at origin. Then the Nyquist contour will be similar. Our aim is to plot this A to B, B C D and D to A. Simple. So let us follow the steps that we have learned in this AB part. Put S is equals to j omega. Then G of j omega is nothing but 1 by j omega plus 1 or j omega plus 2. Then the magnitude will be 1 by under root 1 plus omega square 1 plus, excuse me, under root 1 by 1 plus omega square, here 4 plus under root 1 under root 4 plus omega square. Similarly, phase is, see, you can we have this flexibility in calculating the phase. We can calculate numerator denominator separately. In the numerator phase there is 1, so using the formula tan inverse 0 by 1. Here tan inverse v by a formula. Here 1 by 1 plus tan inverse, you'll get omega by 2 if I'm not wrong. Omega by 1, omega by 2. So now this will become, using tan inverse A plus tan inverse B, that is tan inverse AB by 1 minus AB. After calculation you will get minus tan inverse 3 omega by 2 minus omega square. So now you got phase expression, magnitude expression, varying the values of omega. Find out magnitude and phase. Let us say omega value 0, then you will get magnitude 1 by 2, omega 0 you will get 0 degrees, and let us say omega value 1, then you will get magnitude. After calculation here we got 0.316. Phase we got minus 71.56 degrees. Similar, omega infinity you get magnitude 0, phase minus 180 degrees. Yes, now the important part is here. How should we plot this polar plot? I have already said polar plot is nothing but plotting this AB part. So that too in S-plane. This is imaginary axis, this is real axis. See, here we are plotting in the form of polar form. So we can represent phases, angles also here. This is 0 degrees, this is 90 degrees, 180 degrees, 270 degrees. Coming in the negative angle, this is minus 90 degrees, this is minus 180 degrees, this is minus 270 degrees. So now look at this table, omega. At omega 0, your magnitude is 1 by 2, phase is 0 degrees. So what is the 0 degrees line? This is the 0 degrees line. So your starting point will be here. At what magnitude? Let us say this is 0, this is 1 by 2, this is 1. So at 1 by 2, your starting point at omega 0. Always your starting point is omega 0, your ending point is omega infinity. Now at omega 1 your magnitude is 0.316. That means somewhere here 0.316 at an angle minus 71.56. That means it lies in this region. So you need to come this way. Come this way. And now omega infinity. Magnitude 0. Minus 180 degrees. Minus 180 degrees line is this. So your ending point will be in this line. At what magnitude? 0 magnitude. That means you have to come here. At omega infinity. That means simply draw like this. That is nothing but you are drawing something like this. And now you are drawing something like this. Starting from here, omega value is varying from 0 to infinity. Here omega 0, here somewhere omega value 1, here omega value infinity. And now the most important point is what should be the direction, whether clockwise or anti-clockwise. The process is this: find the phase difference between these two things. Delta phi is equals to minus 180 degrees minus 0 degrees. Phase between starting and ending. Your phase difference will be minus 180 degrees, that is negative. Negative, if the phase is negative, your direction will be clockwise. The phase is positive, your direction will be anti-clockwise. So your phase is negative, so your direction will be clockwise. Just simply plotting the AB part, you will get in S-plane polar plot. Now For the same question, draw the Nyquist plot. Same, but the plane will be g of s, h of s plane. And the same thing we will be drawing here, the same clockwise direction, here omega 0, here omega infinity. This is AB part, right? Now, like what is Nyquist plot? Summation of AB, BCD, DA. So we have done AB part. What is BCD? If number of poles greater than zeros, BCD is point at origin. So here 2 poles, 0 zeros. So poles are greater than zeros. So BCD will be a point at origin, BCD. And now BCD is completed. DA is nothing but symmetric around x-axis. Symmetric around x-axis. So same clockwise direction. This is DA part. This is our simple Nyquist plot. So now the final important thing is stability criteria using the formula n is equals to p minus z. Here n value, as we have discussed it in the starting a number of encirclements. Here the number of encirclements are around -1, 0. So -1, 0 will be obviously here. So project this line upward. There are no encirclements around this line. So here n value is 0, and again p, as I have already discussed, p is number of right-handed poles. So in this, right, p is number of right-handed poles. So here s is equals to, here -1, here -2. Sorry, here +1, +2, but here -1, -2. -1, -2. Here both the poles are left-handed, not right-handed. So in this problem, number of right-handed poles are 0. P value 0. Here P value 0. N is 0, P is 0. Obviously Z will be 0. As I already said you, if Z value is 0, the system is stable. Therefore, the system is stable. This is how you draw this polar plot, Nyquist plot, and find the stability of given system. And now let us do a little bit difficult problem, but there is one more small concept left in this plots, that is, what if there is an intersection across this x-axis? So how to calculate this intersection point? There is a method to calculate this intersection point, that is, anyway we will find phase of the system phi. So now equate this phi to -180 degrees and you will get the value of omega. That omega is known as omega pc, phase crossover frequency. And now substitute this omega in magnitude. That means OLTF, magnitude of omega pc. In this magnitude expression, substitute omega pc and you will get some value. That value is A, and that A is this intersection point. So now we will get this case in this following problem. G of s is equals to s plus 1, s plus 2, s plus 3. Put s is equals to j omega, magnitude 1. Putting s equal to j omega, will get j omega plus 1, j omega plus 2, j omega plus 3, and this magnitude is 1 by 1 plus omega square, 1 by 4 plus omega square, 9 plus omega square. Okay, phase. What is phase? 1 by, this is here tan inverse 0 by 1. Here tan inverse omega by 1. Here tan inverse and plus tan inverse omega by 2. Here tan inverse omega by 3. That is phi is equals to minus tan inverse omega by 2 minus tan inverse omega by 3. So now we got magnitude, we got phase. Now what we need to do is similar steps. that is vary in the value of omega, find magnitude, find phase. Omega 0, you will get magnitude 1 by 6, phase 0 degrees. Omega infinity, you will get magnitude 0, phase minus 270 degrees. And delta phi, phase difference is minus 270 degrees, therefore the direction will be clockwise. So now draw the polar plot. Polar plot means in S plane AB part, that is polar plot. So now 0, 90, 180, 270, minus 90, minus 180, here minus 270. Okay, now at omega 0 magnitude 1 by 6. Let us say this is the magnitude 1 by 6. Obviously 0 degrees line, 0 degrees line. So starting point is this. So what will the ending point at minus 270 degrees line? That means this is the ending, this is the minus 270 line. So here we will be ending at a magnitude 0. That means we need to come this way and go to origin. Starting from here, go to origin. Why origin? At omega infinity magnitude 0. Here omega infinity, here omega 0. So what is the direction? Obviously minus 270 degrees, the phase difference negative, clockwise direction. This is the polar plot. Now what is the intersection point? As we have already discussed the procedure to find the intersection point, equate the phase to minus 180 degrees. So what is the phase here? Minus tan inverse omega minus tan inverse omega by 2 minus tan inverse omega by 3 is equals to minus 180. So minus tan inverse omega by 2 minus tan inverse omega by 3 is equals to minus 180 degrees plus tan inverse omega. So tan inverse A plus tan inverse B, tan inverse A plus B by 1 minus AB. That is taking out all those minuses. Finally removing this tan inverse also, you will get omega by 2 plus omega by 3 by 1 minus omega by 6 is equals to minus omega. You will get omega root 11. This is nothing but phase crossover frequency omega PC root 11. And now find the magnitude at this omega PC. So what is the magnitude expression? 1 by under root 1 plus omega square, 4 plus omega square, 9 plus omega square. So put omega value root 11, you will get magnitude 1 by 60. So this point is 1 by 60. So what is this is polar plot. What about Nyquist plot? Same. G of S plane, H of S plane, same. Redraw this plot clockwise. Here omega 0, omega infinity. This is AB part. Obviously BCD same, point at origin because poles are greater than 0. ABCD point. And what about the other part, DA? Symmetrical form of AB, you will get DA. Done. So in order to find the stability, we need to draw minus 1 projection. But how will we know where the minus 1 is on the x-axis? We know this intersection point is 1 by 60. That is obviously less than 1. So if this is 1 by 60, that means here minus 1 by 60, here minus 1. So we need to project the line here. So there are no encirclement around the point minus 1. So using our formula, n is equals to p minus z. Here n value is 0 because there is no encirclements around this minus 1, and p. See in the question given 3 poles, these 3 are left-handed poles. So p value is 0 because there are no right-handed poles. So now the calculated value of z is 0. Therefore the given system is stable. this is how we'll draw polar plot, Nyquist plot, and find the stability. And so far we have not yet covered the problem which contains EFA, that means those 1 by S, pole at origin. Let us lastly let us do that problem and conclude this topic. Yes. G of S 1 by S into S plus 1, S plus 2. Same. Substitute S is equals to J omega. Find magnitude. G of J omega is equals to 1 by J omega, 1 plus J omega, 2 plus J omega. So what will be the magnitude? Omega 1 plus omega square, 4 plus omega square. What will the phase? Minus tan inverse omega, minus tan inverse omega by 2, minus tan inverse, tan inverse omega by 0. That is nothing but omega by 0 means minus tan inverse infinity. Minus tan inverse infinity means that is minus 90. Minus tan inverse omega by 2 minus 90 degrees. So now getting the magnitude expression, phase expression, wherein the value of omega, find omega magnitude f. At omega 0, magnitude infinity, phase minus 90 degrees. At omega infinity, magnitude 0, phase minus 270 degrees. Phase difference delta phi is equals to minus 270 minus 90. You will get minus 180. So phase difference is negative, direction is clockwise. And now draw the polar plot. Polar plot, S plane, polar plot 0 degrees, 90 degrees, 180, 270, minus 90, minus 180, minus 270, all angles. So now at omega 0, magnitude infinity, minus 90. So what is the minus 90 line? This is the minus 90 line, and infinity means somewhere here. So let us start with some distance, minus 90 degrees line at omega 0, magnitude infinity. So obviously omega 0 will be the starting point. Omega infinity means magnitude 0 in the line minus 270. So it should end in this line at this point 0. So it's a starting point, ending point. Simply draw this way and given direction clockwise. Here omega infinity. This is polar plot. And also here again, once again we have got this point of intersection. So always doing that huge process, it might be time taking for us. So there is a shortcut method in order to find this value of a, that is, take the characteristic equation of the given transfer function s into s plus 1. This is g of s. Find 1 plus g of s, that is, you will get 1 plus k into g of s. You will get s cube plus 3s square plus 2s plus k is equals to 0. Now product of extreme coefficient is equals to product of these two coefficient. That means 1 into k is equals to 3 into 2, 6. This is the value of k marginality. The value of a is 1 by k marginality, that is 1 by 6. This is the shortcut method that I am telling to you. So this again point of intersection is 1 by 6. Obviously it is far from 1, that is the value of minus 1 is here, minus 1 6. See, this 1 by 6 is just magnitude. Don't tell that this 1 by 6 is plus 1 by 6, that's why we have to plot 1 by 6 here. No, here the value of a is only magnitude and the point is here. That means that exact value is minus 1 by 6. So minus 1 is here. And now Nyquist plot. Same, g of s plane, h of s plane. Redraw this here from 0 to infinity. 0 omega infinity. This is AB part. BCD, point at origin. DA. What is this DA? The point, symmetric part of AB. This is AB, this is BCD, this is DA. This point is 1 by 6, minus 1 by 6. So obviously minus 1 will be here. So this is thing. This is Nyquist plot, and stability criteria n is equals to p minus z. Here there are no encirclements for this, so n value is 0. In this given problem also, there are no right-handed poles, all are left-handed poles. So p value is 0. So we got p value 0, we got z value 0. This is system is stable. But one more thing that we have forgotten here is the Nyquist contour here is not in the first case, because here we are having one pole at origin. That means we need to draw this DEF part also. That means A, B, C, D, E, F. Sorry, not D, F, it is E, F here. We have done A, B, we have done B, C, D, we have done D, E, F. So what is left here? E, F, A. So we have already studied that if there is one pole at origin, the Nyquist plot for that EFA is one semicircle. So in this Nyquist plot we'll get one semicircle, the same clockwise direction, because delta phi is that thing, negative. So this is final Nyquist plot.